Yeah. Hello, myself Jeet. I'm working with Ambato the Jawanini. My PhD topic is decoherence in time resolve. My PhD topic is decoherence in time resolved spectroscopies with TDDFT. Its contents. Like first part, I will briefly talk about the foundation and theoretical advancement of the DFT density functional theory and time dependent density functional theory. And part two, I will mostly talk about my PhD project, how we are going to approach our like decoherence processing time dependent density functional theory. And at the end, I will briefly mention my other projects. Part one. So what we used to do in our office, we are actually quantum computational material scientists. So the main goal of our most of the project is somehow to describe material properties from theoretical methods using fundamental equations. So here is the cartoon picture. It's me sitting in front of my laptop inside my office. What we are doing the first principle is ab initio. It means like starting from the beginning without considering any like approximations and all. So what we put as an input, what we did, we put some atomic informations inside the computer. It happens like ab initio calculations, DFT, TDDFT, and some numerical codes. And what we get, bunch of output as a material properties like electronic properties, vibrational properties, structure of the material, color of the material, optical properties. Let's start. This is the beginning. What we are interested in to find the ground state of bunch of electrons, and how to proceed this, we try to solve the Schrodinger equation for the many body systems. Here psi is the many atoms or electrons and nucleus, bunch of nucleus system, and where H is the like many body Hamiltonian, where H consists of two terms. One is the kinetic term and another one is the like potential term, which is the charge interactions. Like we know that if there is two charge, there is always a Coulomb interactions. So we know that in quantum mechanics, basic quantum mechanics, we mostly talk about single particle states. But here we have like lots of electronic electrons, degrees of freedom, nucleus degrees of freedom, and it is quite hard to solve it. So what we have to do, we have to make our problem a little bit simpler. So first we use this Born-Oppenheimer approximations. What it says that as nucleus are big, so it is slow, and electrons are like small and it is fast. So we can decouple the dynamics of this electron and nucleus. So what it means, that decoupling means. So specifically, to get the time requires to get the ground state for the electrons is much faster for electrons compared to the nucleus, because nucleus is very heavy, is quite barely about to move. So we can actually mostly focusing on now onwards on the electronic part of these wave functions. So already like reduce number of degrees of freedom. So here the Schrodinger equation for the electronic parts, where the psi E represents the electronic wave functions and H is the Hamiltonian for the electronic part. The first term consists of three terms. First term is the kinetic part. Second term is the interactions between nuclei and electrons. The third term is the electron-electron interactions. Still, there is lots of degrees of freedom, because in positions means 3n degrees of freedom total, because each spatial coordinates has three coordinates like x, y, z. So still the like to solve this first equations is very very complicated. So like let's take a look at some issues. Like if you consider the carbon dioxide for small cases, we have 22 electrons. The 22 electrons have total 66 dimensional problems. So it's very hard already. So like when you go for like more complicated system like nanocluster of lead, you see that the problem escalates a lot. Like each atom has 82 electrons, and 82, let's say a nanocluster has 100 atoms. So it's like 8,200 electrons, and Schrodinger equation becomes like very big, 24,600 dimensional problem. So we see that solving Schrodinger equations for solid is practically a bit of hassle. It's very complicated. So what we have to do? We have to make even simpler. So now this is the starting point of the density functional theory. In 1960s, Walter Kuhn proved that the ground state of the electronic system can be written in terms of the density as a function of density instead of the wave functions. So what it means, like if you say the wave function has 3n variables, the density has only just 3 variables. So it reduces number of degrees of freedom. So now how to like involve this density to our main theorem? So there are set of very very important theorems that I will just briefly mention. First, Hunenberg-Kuhn theorem. Hunenberg-Kuhn theorem tells us that if you have external potential which is unique functional of the ground state density, means like you have the external potential which is the interactions between electron and nuclei. So then you have the Hamiltonian, you solve the Schrodinger equation, you get all the like states, you find out the ground state, you can calculate the density. So if you know the density, you can get the information of the external potential. So the main idea of this first Hunenberg-Kuhn theorem is that we can use the ground state density as a variable, but it doesn't tell us how to use it. So there it comes, the second Hunenberg-Kuhn theorem. So which is actually a variational principle. So the density which minimizes this total energy is called true ground state density or exact ground state density. So in nutshell, what Hunenberg-Kuhn theorem says that, so we get the ground state density, we can use it as a variable which gives most of the material properties. And the second, that how to get this true density that we are going to use in future. So for practical solutions, what we have to do is pretty famous like Kuhn-Sam equations. So still we have the term of electron-electron interactions, and maybe it's in the next page actually, this many body interactions. So what we have to do, we can do a mapping of like many body interacting system to non-interacting system, which simplifies a lot. So this mapping, we have to do this mapping such a way that the ground state density of the interacting system and the non-interacting should be identical. It is one of the important part. And what they did actually, they replaced the electronic part with Hartree potential. So the Hartree, this is an approximation, but if we take the Hartree potential, means the many body electron-electron interactions, and you consider the effective single body interactions. So then we have, this is not exact, so we have error, and we dumped all the errors into this exchange and correlations. So in practice, if we know the exact form of the exchange correlation, we will be able to solve our density functional theory exactly. So though it is like, so far it is not exactly possible, so we have reliable approximations, local density approximations, gradient, generalized gradient approximations, hybrid functionals. And this is the Kuhn-Sam equations. If we manage to do this mapping from interacting to non-interacting system, we'll get the single body Hamiltonian. So we can easily solve it. Yes. Yes, this R, I forgot to mention this R is also involved the spin coordinates. And there are few softwares that Quantum Espresso, VASP, that can calculate these DFT density functional theories. Though it has a tremendous success, but still it cannot capture the excited state properties of the material, means non-equilibrium properties. So there we have this time-dependent Schrodinger equation, time-dependent density functional theory. So how to start with this? We have to solve the time-dependent Schrodinger equations that I haven't mentioned here. So still the problems is exactly even far complicated than the equilibrium part. So then again we have to take some theorems. That's like first theorem is Runge-Gross theorem. It's 1984. It's a very famous theorem. Like if as it is in time domain, so we have to start from an initial state. So that is if you have a given initial state, then the time dependent external potential you can be uniquely determined from the time dependent density. So it has a one-to-one map. So if you know the density at certain time, you know the external potential that you have. So there is a problem, the Runge-Gross. As you know that there's a variation principle that I mentioned in Hunenberg-Kunz second theorem, and that actually takes care of the energy functional, but here in time dependent, energy is no longer conserved quantity. So they did the quantum mechanical action principle, and they did some mistake. Actually, Gross did some mistake. So, and Leuven theorem, actually, he constructed von Leuven, like properly constructed and derived the theorem, which exactly says this, like we can find a non-interacting system, quantum non-interacting system that evolves on this quantum potential, like it is the like time-dependent version of the static one. Then we can find the density, time-dependent density. This is like time-dependent quantum equation, the time-dependent version of the quantum equation. It's like exactly similar to time-dependent Schrodinger equation, where this psi 0 is your the ground state of the system. And yes, that we got from the DFT. That is equilibrium. And
it's unique.
Yes. And you have the quantum potential, and there is first term is the Hartree, means like Coulombic term, and then external. Now you can see that external term is time dependent. The external term is like external field, electric field, magnetic field, or vector potential, and the Vxe is actually dependent on the action that I talked about, because energy is no longer conserved quantity in time dependent phenomena.
Sorry, the time dependence comes from the fact that you have an external time dependent potential, or it comes from the fact, or
No.
Also comes from the fact that you are stuck out of the equilibrium.
Yes, out of the equilibrium by applying some laser field, strong laser field, like V of x.
For some random theoretical reason, you have started from some out of equilibrium condition and you have no external potential. So can I account for example, for the process of going towards the equilibrium is equation? So if you start from out of equilibrium condition,
Yes, directly.
and you want to know what the typical relaxation process involved, can you use that?
I think so, yes. But I will talk about later, like little bit. And there is also same thing that like we have to design our quantum potential such a way that the density for interacting and non-interacting should be same. And there is few softwares, Octopus, TDDFT, and we are using actually Octopus. This is important. Like, so the first part was gone. So this is my. Now we start about talking about my PhD project. So what we do, why we need specifically decoherence, I briefly mentioned. So first, let's say a material is exposed to a strong laser field. It means like you are driving your electrons from valence band to conduction band, and these excited carriers then undergoes some like ultra-fast phenomena, electron-electron scattering, electron-phonon scattering, and then there is some charge energy redistribution, and then slowly grow to the some equilibrium state or the ground state. This type of like relaxation phenomena is ubiquitous to all real materials. You just excite by some strong laser field, it will go excitations and then slowly come back. So this type of relaxation phenomena is well described in like larger time scale, like is at room temperature, like 100 femtosecond, hundreds of femtosecond. This is the paper, Marco Bernardi. The first paper is the experimental paper. They did some experiment on silicon and they got the result that the relaxation happens in 350 femtosecond. And this Marco Bernardi, they did the theoretical approach. They also got similar type of 350 femtosecond for the relaxation of silicon. But as I mentioned, 350 femtosecond is like quite large, but but this relaxation phenomena is not much explored in the sub-femtosecond theory level. So there are several approaches to incorporate such like relaxation phenomena. Several tools. One tool, first tool is a BSE plus NEGF. Like BSE is beta sulfate equations, and NEGF is like non-equilibrium Green's functions. This is a tool that is very complicated tool. What beta sulfate equation is mostly gives the used for the dynamics of excitants. Like if you excite in materials, then you will get like hole and electron pair. It's called excitants, the bound state of, and they actually go out of equilibrium by solving these non-equilibrium Green's functions. There are several papers, and there is semiconductor block equations. This also mostly used to study the ultrafast properties in semiconductors. This is quite recent papers, though it has not. This is the first one is the experimental paper, which uses the semiconductor block equations for and study some ultrafast properties. And this Isabella Floss is like theoretical paper. They have done both like semiconductor block equation and some other properties, but they are not doing any first principle approach. And for us, we are using time-dependent density functional theory, the Kuhn-Sam equations. And so there is a drawback in Kuhn-Sam like TDDFT, that the TDDFT in general, it cannot capture this out of equilibrium properties because it is unitary in nature and it always possesses some coherent dynamics. Single slater determinant framework cannot capture such non-adiabatic properties, and there is no such natural decoherence mechanism that is involved in TDDFT. So like, so in general, what we want to achieve in our project is that if we shine the laser in the material, that will give rise to some coherent oscillations like this. Means like if we shine a laser, then it will induce some dipole moment. If we go to the frequency domain, this is want to achieve like this dotted curve of the is the like coherent oscillations. After the oscillations, you apply some exponential like post-processing decay, and if you take the Fourier transform, you get this type of plot. So what we want to achieve, we don't want to do this external damping. We want to include some relaxation phenomena inside this like evolutions, and still we want to achieve this type of like the absorption spectrum plot, and which will be like cleared in due course. So to incorporate such phenomena like these adiabatic processes, we used Lindblad formalism, which is white explode in for two-level system for open quantum system. This is like quantum master equations, and where this system actually couples to environment. For us, the environment is like the phononic bath, and we traced out the environment degrees of freedom, then we have the reduced density matrix. So this master equation is well defined for the reduced density matrix. The first terms, this Cohn-Sam Hamiltonian, will actually this von Neumann term that we know already, which is already there in TDDFT, and what we want to add, this dissipator part. So to like incorporate such relaxation phenomena properly. Yes, and here L and Li dagger is a jump operator. So it's defined such a way, this gamma is this scattering time, where like this we define this jump operator in like second quantizations, where Cm is like destroying an electron in band M and creating an electron in band N. So just projecting one band to another band by this jump operator. And for throughout our calculation, we use some like T2 parameter.
The pad is supposed to have many electrons, right? So how do you, is expression?
Yes, so this is for the main, like, and at the end we will sum of everything. It will be cleared in due course, like I have derived an equations for the many electrons.
So, and the density matrix that you have here, how is it related to the density in the theory of DFT?
Yes, like you get your Cohn-Sam states, then you actually construct the density matrix from the Cohn-Sam state.
Okay.
Okay, so in that case, it's a diagonal density matrix.
Diagonal density matrix.
But like, so you always have something that is of diagonal. So when you apply the Lindblad operator, so the idea is always like work separately. So in the part of the TDDFT, but it's going to explain it. It works on the natural orbitals.
Or the diagonal.
On the diagonal, so like it's a diagonal representation of the density matrix, and it's, if you want it to be inflated every time step when you apply this.
Okay, so
This operator.
the off-diagonal term is kind of
Yeah, the off-diagonal term is always like every time step collapse to the diagonal representation. To the natural orbit. So
Which is diagonal in nature.
So it's basically you diagonalize every time, so then the occupation, so the eigenvalue of the density matrix change, and also the eigenstate of the density matrix change, which will be the natural orbitals.
So with every step you have a different type of way of defining the natural orbit.
Yeah.
So you change the
So in reality, so this is a bit technical because you don't need to do it. You need to do it in the specific code that we use, that is real space.
This is not very efficient method because in this approach, like we have to evolve a bigger matrix that is very costly.
Which comes from the DFT algorithm, right?
Yes. Cohn-Sam Hamilton.
Which it's like an effective single particle.
So every time you have to recalculate this.
Because it depends on the density. So like
Exactly.
it's a non-linear.
It's a functional of the density. So
Okay. So basically, how do you start off?
so the DFT
Okay, then you have your
starting point
Hamiltonian, then
and
you feed the.
Then there's some evolution operator that takes care of the fact that Hamiltonian is non-linear. So like somehow stable through this.
Now it's in sort of complete.
so in general the 2D like two-band dissipator is something looking like this, where this off-diagonal term is the main reason behind these decoherence processes, the relaxation processes. We can. This is for now we are just using some empirical data. And
but we want to use like
the electron later I will tell like what we want to do. So like then we extend this two-band approach to n-band systems. We excite the electrons. Then it will like there is some multiple relaxation, like say band 2 to band 3. This 1, 2, 3 is the conduction bands. So this each color signifies the different like scattering processes. This will be a little bit technical, probably. Yes. So probably I should not. Wait, I should not do this thing. It is very. What? Sorry. Good.
share with the entire screen.
This is actually easy to understand.
I'm not sure.
It's not there?
Yeah, share the screen. Share the screen, not the window.
Why it's not?
Share screen.
Yeah, okay. Fine. Click. Fine. Okay. Now it's shared. Should be shared. Okay.
Okay. So for one time step, our algorithm is like this. So we have the full Lindbladian. So then for the one step, we are using split step method, means just or the Trotter decomposition. We separate the the von Neumann evolution part and the dissipator part. And first you use this evolution operator, like e to the power I h k delta t, and then we solve the TDK's Kunsam equations. Then we get the time dependent Kunsam orbitals. And important thing is that for the periodic system, we need to project to this adiabatic basis, which is carrying like more physical properties of your system. You see, it is just like instantaneous eigenstate of your time dependent Hamiltonian. Then you receive this like adiabatic basis.
The underlying assumption is time dependence is local calculation.
Yes. Yes, instantaneous. Like you can, then you construct the density. Then you apply now the dissipator, the Lindbladian dissipator. So for the full time step, you got your dissipation. And now, how do you apply it? By Taylor series expansion. And then you diagonalize the density. You get your renewed occupation and states. And this is one step, and it will like circulate for your total time. Yes, this is the standard.
The way in which you calculate every time variable is different. Because it depends on the decimal. Yeah, that's sense.
I mean, this is standard. The only non-standard way. I mean, this is due to the technicalities of how you represent the wave function, because these are all represented in real space and on a basis, whereas density is represented, the density matrix is represented on a basis, and you need to kind of patch the two representation.
And we are considering some finite states.
That's kind of like standard.
And now, like, we have two different regimes. On TDDFT, we can do linear response when you apply the perturbation is weak, and we can do non-linear response. So now we are doing we are applying some external perturbation which is weak, and later we will be focusing on this nonlinear regime where we can this is the regime where this ultra first phenomenon is happening, where these processes are high harmonic generation, angular resolve photoelectron spectroscopy, transient absorption spectroscopy. This HAG is the 2023 Nobel Prize, like for experimental methods. This they have done for this HAG process. Now, hit the result. So first, I am showing the finite system calculations. So I consider the 4 conduction bands, and the first part is the without decoherence that I shown at the beginning. And when you shine the laser, you will have the multipoles, the dipole moment. So you can see that now you don't have the black curve that I mentioned first. So it will decay using this relaxation time approximations. So Lindbladian approach doesn't guarantee that you will relax to the ground state or some equilibrium state. So you are using relaxation time approximations to thermalize to a which will exponentially go to some equilibrium states.
In principle, so the way you introduce the Lindblad formalism,
yes,
is based on empirical approach.
Yes.
So there's no a priori, no.
No. So far, yes.
Right?
It is purely empirical.
Empirical. So, but if you had to obtain the Lindbladian formalism from first principle, there's one. Usually, there is one basis which is variable.
What 1 year basis something?
There's one base which is sort of the eigenbasis of the main Hamiltonian, which is the favorable basis on which to work for the Lindbladian formalism. Let's say, which is probably what you do already. Right?
Yes.
No, in general, we know that if you diagonalize the Lindbladian, you have the real pattern that actually gives you the lifetime of your oscillations. No, that's you diagonalize your Lindbladian, then you get the eigenvalues, and the real part of the eigenvalues it gives you the.
That's clear. What I'm saying is there are states. I mean, when you the standard approach to quantum optics, where you derive the Lindblad formalism.
Yes.
There is one of the parts of approximation is the so-called secular approximation, which basically you say that there are gains just because they are too high frequency, and they're sort of a Lindblad approximation.
Yes.
We don't do this approximation because we're not
So
because
that,
we want
I
to
think that is something.
Yeah, but there is. I mean,
well, okay, so but we kind of do it.
exactly, because you use the base of this sometimes.
Yeah, exactly.
So that's the reason why it makes sense to use this base, because that's the sort of pointer states towards which the ground of the system instantaneously wants to be coherent.
Because you want to have a notion of which states couple with which other state, and if you have the laser field acts as a gauge, whatever, it's always moving,
So
it's always changing.
Mostly we are working.
But this is a problem only for the solid, I would say. For an atom, two-level system, very isolated system, this like the action of the potential. The gauge field is not doing anything because you can work on a different gauge. That's a difficult one. But for a solid, what happens is that, I don't know, so the state with a given K point, with a given like block phase, if you have the architectural potential, it gets like into the R in K, the phase of the K point, plus the value of the vector potential.
Yes.
And this is the adiabatic motion you want to get out of it, because if
higher to be about the gauge due to the
Yes. So mostly,
Yeah, because what you want to do with the linear approximation is you want to always maintain the notion of which state got there with other states. So this, the matrix that you define is always within the basis, and you like these states talk to each other. If you kind of your basis change definition, you character under yourself, then you're not doing what you do.
so as you mentioned, like we are working on the velocity gauge, so we have
it's one
in this instantaneous basis actually.
These are the instantaneous basis of the function of the Hamiltonian with the heaven like this is the adiabatic basis if you want. It's the closest feature of the
Yes.
which makes sense from the what would you do to know what the problem is?
Yeah, but you can derive these equations like in solid state physics, you can derive it from principle. Yeah, you can draw it. Yeah. So you have to,
You have to construct the jump operators that monitor the interaction with the energy levels of these two levels are more energy separated.
Yes.
Yeah. You can truncate this.
You have to, yes.
Yeah. If this comes out, of course.
This type of scattering, I think, is forbidden. Like, if the energy level between two energy level has to like differ like hugely, then we have to neglect that transition. Yes. And then this is the like dipole moment, and if you take the Fourier transform, you get the absorption spectrum. And as I saw that, as this basis is not complete, we are truncating the basis. So there is like this. We have seeing this some peaks. Like the more you propagate, the more it shrinks. It has like sometimes infinite lifetime at the end. Like if you add more number of states, like as I mentioned that I used 4 conduction bands. If you take more conduction bands, then it will be like fully matched with your reference calculations.
So basically, this wiggles there becomes.
Yes, this is coming from this. Yes, this is coming from the like delta kicks. If the delta kicks is like sync nature, the wiggles is coming from that. And this is for the finite system, and now the this is for this. I performed the calculation for the bulk silicons, and we applied the like very weak delta kick. The 4 conduction band, and we see here is as dipole moment is not properly defined for the bulk system, so we calculate the total current of the system. And if we noticed, if we take the Fourier transform, like it has very good agreement with the silicons. But if we take more number of K points, I have considered the only 12 K points. If we take more number of K points, I hope it will converge more. No, the rate curve is the like after the simulations, you are applying post-processing phenomenological damping, exponential damping at the end.
So the red curve represents like some dipole oscillation. So the our oscillation, the dipole after perturbation. And then like in a purely coherent system, it will go on forever.
Forever.
You multiply the black line with this. you're gonna have like some damping.
Post-processing damping, yes, after the simulations. And then you take the Fourier transform, you notice that it's almost matching. But if you introduce more number of K point, I hope so, it will still, there's nothing new. So still this process is not first principle approach. So what we want to do, like we want to incorporate this, this is the paper, this archive paper, they are doing some HAG high harmonic generations. And they mentioned that electron-phonon coupling is one of the main reason behind this decoherence process. And this electron-phonon can be calculated from density functional theory, perturbation theory. And then we want to introduce, like, we want to make our approach more general. And then we'll try to bridge this theory with some experimental technique like palm probe, RPS, HHG. And the applications I think will be to study the excitant dynamics, which is quasi-particle. Like if we apply some circular light, there are like in 2D materials and TMDs, you have K and K prime valley. Valley means like you have local minima except the gamma point also. So when you apply this circular polarized light, the intervallous scattering is happening, and intervallous scattering, to study the intervallous scattering, we need this relaxation phenomena. I don't know much about this, and there will be another application. We would like to study some steady state properties of the periodically driven system flow cat, and probably I don't know much, probably RPS, there is some momentum dependent King structure, anomalous lifetime, probably for that we would like to explore this relaxation phenomena. As I mentioned, we are working in octopus and this Chang Wei, his postdoc, and this is my another projects. Like I'm quite interested in diverse fields like this. I'm doing van der Waals interactions in Casimir physics. So what I did, I calculated the van der Waals interactions for different geometries. It can be conducting, it can be dielectric. There are a few published papers, and here I'm writing a book in preparations. It's like focusing on the semi-classical theory of the dispersion forces. That's all. Thank you.
With your alternative approach, you consider having so typical setting which you have, for example, a pulse.
Yes. Yeah, like yes, like this is the like one of the thing. Like you poke the system, you want to like see the like what happens in a later time. It's the response functions, and mostly we study in the like Fourier domain, like Fourier
Although
space.
response function does depend on the what it applies for a week.
It depends on like which type of perturbations you are applying, like strong, weak.
So then you could apply our approach, which is sort of a 2D spectroscopy. So you're basically using two variables in this case. So you are using the length of the pulse and the length.
That's called like palm probe spectroscopy. One will be very short, and there will be one will be quite long. I mean, just one to excite, and there will be another which will propagate the systems like palm probe spectroscopy.
Yeah.
Two photon experiments.
Yeah, in general, yes. No, what I'm saying is that you can access much more information using this 2D spectroscopy
Yes.
rather than linear response, standard linear response.
Linear response is we're just truncating them. If we linear response can be considered as like time-dependent density functional theory, or the time-dependent perturbation theory. You cut it to the first order. That's it. Yes. Not much about non-linear regime.
The idea is to study the dynamics when you create some excitation. You create like some, you come with the laser, you create,
Goes
you pump electrons into some event, and it scatters and do stuff.
That will be like, we want to study in this regime, like the strong, the ultra fast regime, like few
This you can
femtoseconds.
also build a linear response, time-dependent linear response, what it's talking about. So that you come with the problem, then you probe linearly, you calculate it.
The response is much less than what it is.
Oh, no, it just simulated.
You don't see excitations, higher excitation.
No, it's pumped, it's time results, yes. But you come with two lasers, as you were saying, or you two photons, like one is creating some excitation and the other is probing the system quickly. So if it has to probe, it doesn't have to. So that in this case, it's time resolving.
Yes.
But it doesn't matter, right? So for this thing, you can do whatever you want. But like, it's mostly interesting to have the dynamics that is properly accounted for, the electron dynamics. And electron dynamics, electrons in solids, they mostly do stuff with phonons. So like, that's what
You distort the lattice, you get the phonons there.
You want to include some kind of a way to account for the electron phonon
So now,
interaction in time.
yes.
When you go to, now you said you want to extend it to look at picture, right?
Yes, also
In future, we want to study also the.
In fact, I don't know how long line you're approaching okay. Because I don't even know what it means to look at the blood. All those secular approximations we were discussing about. I don't know whether.
no, but yeah, it's just a different. So a flocade purely works like if you have an exactly time dependent, time periodic Hamiltonian.
But
But you can still apply this approximation on, which is idealized on the case when you just apply the methods you implement and you use a laser that is periodic and then you probe your system in this condition.
is it still valid or the approximation you do like this adiabatic approximations and so forth?
But this has nothing to do with flocade or not flocade. This has to do with the time-dependent Hamiltonian. So this is valid to the degree in which like well, okay. So the main engine of change is an external laser field. So in this case, it kind of works. It's a good approximation. So there are better approximations. So this time-dependent basis, this instantaneous basis, it's just to account for the trivial, like adiabatic motion, like of the electron into the band, but still have some spurious effect, some interband contribution that, like, it just represented thing to this basis that it's not correct. So, for instance, you would have like wrong.
It's the gauge that you are.
Yeah, exactly. So I mean,
essentially very
very phase is wrong. So you need to account to correct for this very phase somehow. The very phase actually it's automatically included if you use this adiabatic base because you diagonalize the Hamiltonian. So these guys are always.
But unless you go back into the original base, that accumulates.
Yeah, exactly. But so. There is a way to, so it's all about the phases of this basis. That it's for a solid, like screw things up, and it's tricky in general. So they're we kind of want to explore what is the best time-dependent basis to work with. But we don't know for sure.
We implemented call this is like adiabatic basis, like it's part of Houston orbitals. We just remove the phase part. It's tricky to handle. That's tricky to handle it. And the gauge should be in the velocity, so we no need to integrate in the phase also. Velocity gauge quite easy to handle, and when the like length gauge is hard. electric field pulse, your positions. So, and I think it would matter also because you are working in a periodic, lattice is periodic, so it can make some changes in your, if your system is like a 1D or 2D materials, then it has some other symmetries that can be broken.
If there's no other questions, thanks for being here again.